Okay, so I want to look at some fairly simple, straightforward examples of Newton's second law. We talked about the first law, second law, third law. So really our focus is going to be on the second law and how we can solve some simple problems at first, and we'll make it more complicated eventually using Newton's second law. We're going to be frictionless. We're not going to have any friction in these problems. Eventually, we'll introduce friction and some other things. So let's recall the second law is the net force acting on an object is equal to its mass times its acceleration. Another way to write this is the sum of the forces acting on an object, the vector sum, is equal to ma. And the way we'll do this is we'll set up a coordinate system. We'll look at the forces acting in the x direction, the forces acting in the y direction, and we'll analyze both directions separately. Okay, so the first thing I want to look at is an object. Let's say you have an object sitting on a table. Big mass M. And connected to the table is a little pulley and a hanging mass, little m. Okay? We're assuming that this is frictionless, that the pulley itself is massless, frictionless. So we have this magic pulley and we have a magic string, okay? So there's a string connecting little m and big M. And the string doesn't stretch, it doesn't have any mass, or we can say that the mass of the string is negligible. Say this is a fairly large mass, this is a large mass, okay, of some kind. So the string's mass is very negligible compared to the mass of the system. So I want to look at the forces acting on the big mass and the little mass and talk about them separately, okay? That's the way we're going to analyze this. But what's going to happen with this system if there's no friction? Let's say that the system starts from rest. Well, obviously, this mass is going to begin to fall, and this mass is going to slide along the table, okay? This is under the influence of gravity, so there's a force acting here due to gravity. Then there's also a force along this string. That force all along the string we're going to assume to be equivalent. Okay, so the string itself is just redirecting the force. All right, the magnitude of the force along the string is the same everywhere. So whatever force, which we'll call tension, is acting at this point is the same tension or force acting at this point. So we set this up, the system starts from rest, this mass begins to fall, and we're going to calculate the acceleration of this system using the second law. So the first thing I'm going to do is I'm going to look at the forces acting on big M. So I will draw what I'll call a free body diagram. So I'll take this big mass out of its environment and just look at the forces acting on the large mass. Well, we know that there is a force due to gravity acting in this direction, down. That's big mg. That's the large mass times the acceleration due to gravity. There's a normal force acting on this object. I'm not going to put the vector arrows here. That's the arrow, meaning it's a force, okay? So there's a normal force, that's the table pushing back up on that large mass, a contact force between the mass and the table. There's also this force of tension acting in this direction. I'm going to call that big T for tension. Any other forces acting on the large mass? I don't think so. Let's look at little m. So little m, there's little m. The forces acting on little m are little mg and tension. The magnitude of these two tensions is the same, just like I explained a few minutes ago. We're assuming that whatever tension is in the string, that tension is equal all along the string. The magnitude is. Okay? So I'm going to set up an XY coordinate system for each one of these masses. And for this one, in this case, it's pretty simple. That's X and Y. For this one, it's the same thing, X, Y. No big deal, okay? So let's look at the big mass first. So we've got the free body diagrams. Now we can analyze, using Newton's second law, we can analyze the forces acting in each direction. So let's look at big M. Let's look at the X direction first. So we sum up the forces in the X direction. Well, it's simply T is the only force acting in the X direction, and that equals big M-A-X. Okay? That's the acceleration in the X direction for big M. For the Y direction, we have the normal force is positive. So I'm just summing up the forces. This is the gravitational force, that's negative. That's going down, that's in the negative Y direction. And that equals a Y. But I know that this is sitting on a table. There's no acceleration in the Y direction. This object is not accelerating up or down. Okay? This is equal to 0. So the Y direction is very simple. Okay? In the Y direction, there's no acceleration. So the normal force here, we can solve this. The normal force is just equal to mg. That's the magnitude of the normal force. Obviously, the normal force is in the opposite direction of the gravitational force. Okay, let's look at the forces acting on little m. So for little m, that's the negative y direction. That's the positive y direction. So I have T is T minus mg is equal to m-a-y. Okay? That's equal to m-a-y. Now, in a lot of text, in a lot of places, you do a lot of bookkeeping, or what I call bookkeeping, where you make some relationship between AX and AY. Okay? So in this case, AX would be equal to negative AY. So meaning if it's accelerating in the positive X direction, that's an acceleration in the negative Y direction for this mass. Okay? Little m. All right. Here's the way I do it. I set up the acceleration. I know that if this object is accelerating in this direction, right? Let me go ahead and get rid of these coordinate systems. Okay. I put one acceleration for the system based on the physics. So for this mass, this is the positive acceleration direction. And for this mass, this is the positive acceleration direction. Okay? That makes it a little easier if I use this as the positive acceleration direction, then I can change this around and say that mg minus t is equal to ma. This is what we always do. The forces are equal to ma, the sum of the forces. This one I've already got set up. That's the positive acceleration direction. So that just says that t is equal to ma, big Ma. Okay? That way, when I want to solve for the acceleration, I have a common acceleration between the little mass and the big mass, and I don't have to worry about. Okay, so I have the large mass. I'm giving it a positive acceleration in this direction just because of the physics, and it makes the calculation a little bit easier. And the smaller mass, the positive acceleration is this way. So in this case, I just have t equals big Ma. Over here, mg is positive. Due to that, I'm calling that the positive direction. mg minus t is equal to ma. Okay? So I'm going to put these two together because I want to solve for the acceleration. So I will replace t in this equation with big Ma. Two equations and two unknowns. So now, replacing that t, I have little mg minus big Ma is equal to little ma. Now I can move this around to solve for a. I'll do that. And you get little mg is equal to little m plus big M A. What is this in this form? This is the net force acting on the system. The net force on the system is little mg. This is the total mass of the system, little m plus big M, times the acceleration. That is Newton's second law. Net force, total mass, acceleration. So solving for the acceleration, that's pretty simple. That is A is equal to little m over little m plus big M times g. Okay? It's some portion of the acceleration due to gravity. It's that ratio of little m to little m plus big M times the acceleration due to gravity. Now, I have the acceleration. If I want to solve for the tension, all I have to do is remember that tension is equal to big Ma. So I can replace I can replace A with this and solve for the tension. So the tension is equal to little m big M over little m plus big M times g. This is the kind of thing we're going to do in all of these problems. We're going to Look at the physics. Try to figure out what's going on. Set up some coordinate system. Draw free body diagrams and analyze those free body diagrams. Look at the forces acting in the x direction, forces acting in the y direction. And then we can use some algebra to solve for the accelerations, solve for the tensions, whatever it may be. So I want to look at another type of system, the inclined plane. We're going to do a bunch of problems based on objects moving up and down inclines. A ramp, an incline, same kind of thing. In this case, it'll be frictionless. Eventually, we'll introduce friction and some other things along the incline. But right now, I just want to look at a simple inclined plane. So here is an inclined plane. Let's call this angle theta. Okay? Typically, you call the smaller angle theta. It's not, you could use theta here, but we're going to call this angle theta. And let's say there's an object sitting on the plane of mass m. Okay? No friction. So let's look at the forces acting on this object. Well, there is, put the forces in red. We know that there is a weight, a force due to gravity, and it is down. This inclined plane is sitting on a flat surface. I know I drew it like it's floating in the air, but it's not. It's sitting on a flat surface. So what we're going to do is we're going to break these forces up into forces perpendicular to the plane and forces parallel to the plane. It makes the problem easier because this object is moving along the plane. Okay? It's not moving in this direction. We don't really, that direction isn't going to matter a whole lot for us right now, but it will make a difference when we start talking about friction because those friction forces between the little mass and the incline will depend on that normal force for us. Okay, so I'm going to break this up into components. A component that is perpendicular to the plane and a component that is parallel to the plane. That's this force. Okay? That's this little mg broken up into a component perpendicular to the plane and a component parallel to the plane. All right? I claim, let me redraw it a little bit differently just to show you how these angles work. So this is mg. That's this force, okay? That's this force is little mg. I'm going to move this down to here. I'll shorten this just a little bit to make it look better. Okay, so I'll move this force down to here. That's not too bad. That's the force acting along the incline or parallel to the incline. I claim this angle is theta. We could do some analysis. We could do some old-fashioned geometry and look at parallel lines and perpendicular lines to prove that that angle's theta. But here's the way I like to think about it. If, as you say, this was on a little hinge right here, and I could move this plane up and down. This vector stays in the same direction the whole time. That's the force due to gravity. That is always perpendicular to this bottom edge. Okay? So it's sort of just hanging like this. As I move this up, this component starts getting farther and farther this way, and this angle gets larger and larger. So as this angle gets larger, so does this angle, the angle between that perpendicular component to the plane and the force due to gravity. Okay? As it gets smaller, as the angle of the incline gets smaller, this starts to come together and get smaller as well. So they follow the same trend as they get larger, smaller. I claim that this angle is theta, just like this angle. Okay? If you want to go through the math or the geometry and prove it, that's fine. So let's look at these components with this angle theta. This is the hypotenuse of the triangle. This makes a right triangle. This is a right triangle with that side being the perpendicular. Okay, that's not so great, but that's a little bit better. That side is the 90-degree side. This component is mg cosine theta. That is adjacent to theta. This component is mg sine theta. That component of the force due to gravity that's parallel to the plane is mg sine theta. The perpendicular component is mg cosine theta. Those are magnitudes. We'll have to keep up with the direction depending on which way we define our coordinate system. Okay? That component that is parallel to the plane is mg sine theta. That component that's perpendicular to the plane is mg cosine theta. All right, you need to commit that to memory so you don't have to derive it every time, but this is the way you derive it. All right, so let's do a free body diagram and look at the forces acting on this mass. I'm going to make the coordinate system along the incline. I've already broken those forces up along or parallel to the incline and perpendicular to the incline. So I'm going to just make my coordinate system go along the incline. So I can look at parallel forces and perpendicular forces. So here's the free body diagram. Here's little m. Here's my little coordinate system that I'm remembering. Okay, just our normal coordinate system. So I have mg sine theta in this direction. That's this force. Mg cosine theta in this direction. That's this force. That's that force perpendicular to the plane. This is the force parallel to the plane. Then the normal force. That normal force is acting, if you want to think of it as the contact force or the normal force, okay, it's acting perpendicular to the plane. No friction. All right. So we can analyze the acceleration of this object along the plane with Newton's second law. Let's look at, I'll get rid of this. Let's look at the sum of the forces in the x direction. So in the x direction, We always have sum of the forces is equal to MA. So, if up the plane is positive, we have minus mg sine theta. That's the force acting on the object along the incline or parallel to the incline. And that is equal to little ma. Okay, I'm making A positive. This will be the positive acceleration direction. Nothing strange about that. That's the positive x direction. In the y direction, we have up will be positive, down will be negative. The normal force minus mg cosine theta is equal to ma, and I will put a y on that. But there's no acceleration in the y direction. This is not falling through the incline or leaping from the incline or anything like that. So this one's simple. The normal force is equal to mg cosine theta. That's all that's happening in the y direction. The magnitude of the normal force is equal to mg cosine theta. In the x direction, we have minus mg sine theta is equal to ma. The m's cancel, and it says negative g sine theta is equal to a. And you may think of this as ax. I just call it the acceleration parallel to the incline. That's along the incline. Galileo knew this. This is the crux of that acceleration along a ramp experiment that you should have watched by now. Okay? The acceleration is equal to minus g sine theta. Okay? It's independent of the mass. Any mass that you put on the incline, independent of the mass, and ignoring friction, you will get an acceleration that is equivalent to g sine theta. Okay? All right, so let's look at a problem based on this. I'm going to set it up like I did the previous problem with the object on the table. Only this time I'm going to let the object be along an inclined plane. So here's big M, just like we had on the table. And here's our little massless, frictionless pulley. And hanging from that pulley is little m. Okay? Still have the big mass and the little mass. All right? I'm going to go ahead and define these acceleration directions for both of these masses, and that way it helps with some of the algebra. I don't have to worry about negatives and positives in bookkeeping. I'm going to say up the incline is positive. That's the positive acceleration direction, and this will be the positive acceleration direction for little m. Okay? Next, free body diagram. Let's look at the forces acting on big M. Well, it's exactly what I had before, except now we've got this string attached to this little mass that's hanging, okay? And I'm going to start the system from rest. Doesn't have to, but that's the way we're going to do it, okay? So we have the normal force. This force is big mg cosine theta. That's that force this way. The force that's down the plane is big mg sine theta. Okay. Then there is a tension force due to the pulling force of the string. Okay? If you need to sketch your forces out on here, that's fine. All right? But this is a free body diagram for this mass that's on the incline. I know from what I did previously that that force that's along the incline is mg sine theta. The one that's perpendicular to the incline is mg cosine theta. Let's look at little m. Little m's pretty simple. There's a tension force here and little mg going down. Okay, nothing strange about that. Now I'm ready to write down the sum of the forces is equal to ma. So let's look at big M. In the y direction, I'll dispense with that very quickly. In the y direction, F normal is equal to big mg cosine theta. There's no acceleration in this direction, so those forces are equal, or the magnitude of those forces is equal. In the x direction, or along, or some people say, you know, the parallel direction. I'm just going to say in the x direction, I said that up the incline was positive, so I'm going to make this force positive and this force negative. T minus mg sine theta is equal to big Ma. That's the net force, that's the mass times the acceleration. For little m, down is positive. I said that I'm going to make that acceleration positive going this way. So for little m in its y direction, it only has one direction. It really doesn't matter what you call it. You have mg minus t is equal to little ma. Okay? Net force, that's mg minus t, and that is equal to little ma. All right. Now, we do the same thing that we did before. I'm going to break. We're going to, I want to solve for the acceleration of the system. So I'm going to solve one of these equations for the tension and plug it into the other one and solve for A. Doesn't matter which one you do, I'll solve this one for T and plug it in here, okay? So using this equation, I get T is equal to mg minus ma. Okay, that's just moving these around and solving for T. I'll plug that into this equation. So second line. Now we have little mg minus ma. That's plugging in here. Minus big mg sine theta is equal to big ma. Okay. So I just plug that one equation into the other. Now it's just a matter of moving this around and solving for A. Solving for the acceleration. So I have little mg minus big MG sine theta is equal to little m plus big M A. My m's are getting closer together. Oh. Little m, big M. Okay. Little m, big M. Let me move this around just a little bit, and you get little m minus big M sine theta times G is equal to little m plus big M A. And all of this is running together. Get rid of this. Okay. Same thing we had before. There, this side is the net force acting on the system. In this case, you have the gravitational force due to the hanging mass, but you also have that gravitational force that's acting on the big mass because it's on an inclined plane. So it's the difference in little m and big M sine theta times G. That's the total mass of the system times A. Rewriting it again in terms of, or solving for A, you get little m minus big M sine theta divided by little m plus big M all times G. Okay? I said the system's going to start from rest. Well, if the system starts from rest and little m is greater than big M sine theta, remember sine has values that are always between, well, -1 and 1. But for us, with the way we define theta, sine has values between 0 and 1. Okay? So this is little m minus big M sine theta. If little m is greater than big M sine theta, you get a positive acceleration. The system starts moving and the object on the incline starts going up the incline. If big M sine theta is greater than little m, what's going to happen? That gives you a negative in the numerator. That means that the big object is going to pull the little object up. So the big object that's on the incline is going to slide down the incline and pull that hanging mass up. That would be a net negative acceleration. What happens if little m is equal to big M sine theta? That's balance. The objects are perfectly balanced and they're not going to accelerate, okay? Starting from rest in a perfect world, they would just sit there. All right? So that's the idea of an object on an inclined plane with a hanging mass. And we'll eventually introduce some friction into that and do some other things with it. Okay. So that's two nice examples for today. I have posted the WebAssign Chapter 5 homework, and tomorrow we will go more into Newton's second law and look at some other examples and do some numerical examples. And I'll also go over the test. So have a nice afternoon.